In this video, we find area using the limit definition. I will state a theorem involving limits of upper and lower sums, the same upper and lower sums that we talked about in the last video. And then we will define the area of a region in the plane by using limits of upper and lower sums. So let's start by reviewing. The upper sum S sub n is defined this way. Basically what we did was we took this interval from A to B and we subdivided it into n subintervals of equal width. So we made n of those, and the width was delta x. So we take that interval from A to B, we divided it into n equal pieces, and so each piece has a width of delta x. To find the upper sum, what we would do is find the maximum value of the function on that interval. So on this little interval, the maximum occurs at the left. And we evaluate the function there, and we draw a rectangle. And because the function's decreasing, the maximum also occurs on the left over here. So we draw another rectangle, and another rectangle, and another rectangle. And after we're done, we add the areas of those rectangles. So the area of one of these is the maximum value of the function. So that's represented this way. This m sub I is just the x value that corresponds to the maximum value of the function on the ith subinterval. We take it and we multiply by delta x. That's giving us the area of that first rectangle. And then we compute this area and compute this area and compute this area, and we add them all together, and that gives us the upper sum. So the upper sum corresponds to the red rectangles in my picture. Now for the lower sum, I did pretty much the same thing. I create n subintervals of equal width. The equal width is still delta x, which comes from taking that length of the subinterval and dividing by n. And then instead of finding the maximum value of the function on each subinterval, we find the minimum value of the function. Now because I drew a function that happened to be decreasing, the minimum occurs on the right. So we evaluate the function on the right, at the right endpoint, and then we draw a rectangle with the appropriate height. And we find that area. And then we find that area, and that area, and that area. And you can see this is an underestimate of the area under the curve. Now, try not to be distracted by the red rectangles. You see that the area of this blue rectangle misses some of that area under the function y equals f of x, that black curve. So we've missed some area there, and we've missed some area there and there and there when we calculate the areas of these rectangles. But those are the lower sums. Now the true area is somewhere between the upper sums and the lower sums. The upper sums are an overestimate. We always count a little bit more area than is truly there on that subinterval. And the lower sums are an underestimate. So the actual area is in between the lower sums and the upper sums. Now here's a theorem. It's a very important theorem, and it's usually proved in advanced calculus. This is great. It tells you exactly how you can find that true area. Well, actually, it doesn't tell you that. The next thing tells you that. It says, let f be a continuous function. So we've got a continuous function, and it's non-negative. That just means it's allowed to be 0, it's allowed to be positive, but it's not allowed to be negative on the interval from A to B. In that case, then the limit as the number of rectangles goes to infinity of the lower sums is equal to the limit as n goes to infinity of the upper sums. Or that's what the limit of the lower sums looks like using that summation notation. That's the limit of the upper sums using the summation notation as well. And And this is great because our true area is squeezed in between these two guys. So as n goes to infinity, this approaches a number. And as n goes to infinity, this approaches a number. So what does that mean? That the true area lies in between them. And if this is approaching, let's say 7, and this is approaching, let's say 7, well, then the area must be equal to 7 by the squeeze theorem. So those are that's the super exciting implications of this. The true area must be equal to that limit. So if these limits are the same and they're equal to L, the true area must be equal to L. And it also tells us something else. When I'm trying to find the area under a curve like this, where y is equal to f of x, and f of x is always positive except possibly 0 on some interval, I could pick the left endpoint, I could pick the right endpoint, it doesn't matter. I can pick any x value. Any x value would be fine. If I take the limit as the number of rectangles goes to infinity, it's still going to give me the right area. Because if you choose the x value that gives you the minimum values, that works. If you choose the x value that gives you the maximum values, that works. Any x value in between will work as well. So those are our implications. The true area is equal to that common limit, the limit of the upper sums and the lower sums. And we can choose any x value we want. In the ith subinterval. When we do, if we take the limit as the number of rectangles goes to infinity, that's going to give us the exact area. Okay, so this is our definition of area of a region in the plane. It says let f be a continuous function, and let's say that f is greater than or equal to 0 on the interval from a to b. Well, then the area of the region bounded by y equals f of x equals a, x equals b, and the x-axis is given by this. So here's y equals f of x, here's x equals a, there's x equals b. If I want the area under that curve, all I have to do is take my interval from a to b, subdivide it into n subintervals of equal width, so delta x is always b minus a over n. On each subinterval, pick an x value, any x value you want, evaluate the function there. You could choose the left endpoint sometimes, you could choose the midpoint, right endpoint. You could go 2/3 of the way over. You could mix it up, do a combination like I did. If you take the limit as that number of rectangles goes to infinity of this sum, you're going to get the exact area under the curve. The exact area. Okay, so in order to use this, we need these requirements. Delta x is that b minus a over n, so that's that equal width of those subintervals. X sub 0, that's where we start. X sub n is where we stop. And all the x's in between come from adding delta x. So x sub 0 is here, x sub 1 is a plus delta x. X sub 2 is a plus delta x plus another delta x. A sub 3, or x sub 3 is a plus delta x plus delta x plus delta x. So I've added 3 of those this time. So that's our formula. Now this looks cryptic, but it's really not. This is just saying that x sub I star, that's a particular x value in between these two x values. So this subscripts make it look more complicated than it is. This is just saying that x sub I star is a chosen x value, any chosen x value, on the ith subinterval. And that's nice because now you can choose the x value that makes this as simple as possible, and then evaluate the limit of that, and you'll know no matter which x value you choose, you're going to get the correct area. I think this is great. So let's find the area of some regions using this fact. And we'll actually start with this region that we talked about in the last video. In the last video, we were looking at the area between y equals 3x squared plus 1, x equals 0, x equals 2, and the x-axis. And we found the upper and lower sums. The upper sum with n rectangles turned out to be this, and the lower sum with n rectangles turned out to be that. Well, according to what we just talked about, the limit of this and the limit of this should be the same thing. I think we can see it already. The true area is the limit as n goes to infinity of either one of those, s sub n, so I'll just use the lower sum, and as n goes to infinity, that goes to 0, that goes to 0, and we get 10. Well, we should get exactly the same area if we use the upper sums, according to our theorem. If we've done everything correctly, we always get the same answer. If you don't get the same limit for the upper sums and lower sums, that doesn't mean that the theorem is wrong. It means you probably made an algebra error somewhere. So this is 0, and that's 0, and we still get 10. So what does that mean? That means that area under the curve is 10. Like 10 what? 10 square units, where 1 unit, or 1 square unit is this 1 by 1, whatever those, whatever 1 unit is in the x direction and y direction. It's 10 square units right there. Okay, so now let's find area using the limit definition for a different problem. And often this is called area under the curve, but what we really mean is the area between the function, the x-axis, x equals a, and x equals b. So we'll say find the area under the curve given by y equals, let's say 25 minus x squared on the interval from, let's say, 1 to 3. And what they mean by that is the area between this function and the x-axis on the interval from 1 to 3. Always start by sketching. Well, that's a parabola facing down, raised up 25 units. So this is not to scale. When y is 0, x is plus or minus 5. So we're going to see something that looks like this. And x is between 1 and 3. So we want that area right there. Oops, it's not supposed to go below the x-axis. It's that area right there. Now you can use left endpoints, right endpoints, you can use midpoints if you wanted to, it doesn't matter. But you want to find either an upper sum or a lower sum for this. And then you're going to take the limit as n goes to infinity, and that's going to give you the area under the curve. So let's start by computing delta x. So I always start by sketching the region, so I know what it is I'm looking for. And then I want to compute delta x. Delta x is b minus a over n. So that's 3 minus 1. That's my a, and that's my b over n. So it's just 2 over n. And then you want to choose a formula for x sub I star and then evaluate it. Yeah, and the way you're evaluating it is by substituting x equals a and the delta x that you just computed. So you've got several formulas. And I think the right endpoints were the simplest. X sub I star's formula for the right endpoints is a plus delta x times I. The other one had an I minus 1 in it, and that would give us 3 terms for our x sub I star. We'd prefer to have as few terms as possible for x sub I star. So we'll just use this one. And this time a is 1, so we substitute that in. And this time delta x happens to be 2 over n, like it was in the last video. So we've got 1 plus 2 over n times I. Okay. And now you want to find the area of one of those rectangles. So that's just f evaluated at x sub I star times delta x. And our function this time is 25 minus x squared. So you've got f, or a sub I is f at x sub I star times delta x. And your function is given to you. So that's 25 minus x squared. X is 1 plus 2i over n. We're squaring that. And then delta x was 2 over n. So you want to write this twice in FOIL. First times first is 1. Outer times outer is 2i over n. Inner times inner is the same, so we'll have 4i over n. Last times last is 4i squared over n squared. You want to multiply all of that by 2 over n. So I would distribute the negative. 25 minus 1 is 24, minus 4i over n, minus 4i squared over n squared, and then distribute the 2 over n to everything. And that's 24 over 1 if you prefer. So we get 48 over n minus 8i over n squared minus 8i squared over n cubed. That's a sub I. And then you want to add those up to find one of our sums. So we're finding an approximation for the area using n rectangles. And we used right endpoints in this case. So the area is approximately the sum as I goes from 1 to n of those a sub I. That's area 1 plus area 2 plus area 3, all the way through area sub n, the nth area. Well, in order to evaluate that, we need to substitute in a sub I, and that was this right here. Okay, and now I've got 3 terms. So using properties of summations, we can break this up into 3 pieces. You want to factor out that negative 8 over n squared. Factor out the negative 8 over n cubed. And then this we've got a rule for, that we've got a rule for, and this we've got a rule for. That's just a constant multiplied or added to itself n times. Gauss gave us the identity for that, and then we had another identity for that. So we've got 48 over n. It's multiplying itself n, or adding to itself n times, so it's just 48 over n times n. And then we've got the 8 over n squared there. And the sum as I goes from 1 to n of I is n times n plus 1 over 2 due to Gauss. Thank you, Gauss. And I've got an 8n cubed over there. And the I squared is n times n plus 1 times 2n plus 1, all divided by 6. So that is our formula for area, but it just hasn't been simplified yet. So let's simplify it. The n's reduce here. One of the n's will reduce here. One of the n's will reduce there. 2 goes into 8 4 times. We could divide this by 2 and get 3, divide that by 2 and get 4. So we end up with 48 minus, it looks like 4 times the quantity n plus 1 over n. And over here we've got 4 times n plus 1 times 2n plus 1 all over 3n squared. Now we want to take the limit of this as n goes to infinity. We could get a common denominator, but that's not really necessary. I'll show you a slightly different way to evaluate this limit. I think it's a little slicker myself. I prefer it. So we're trying to find that exact area under the curve. So we'll compute this limit. Area is the limit as n goes to infinity of that sum that we just found. So we've got the limit as n goes, area is the limit as n goes to infinity of this There are lots of correct ways to calculate this limit. I might factor out that 4. And then just divide that n plus 1 by n. N divided by n is 1. 1 divided by n is 1 over n. Over here, I take out that 4 thirds. And let's split this into 2 factors. You don't have to do it this way. You can distribute and then divide everything in the numerator and denominator by n squared. That's what we've been doing. But here's a slicker way, I think. This is an n squared in the denominator. So let's take the first factor here and divide it by n, and then take the second factor and divide it by n. Notice if I multiply straight across, this times this times this is my numerator. This times this is my denominator. So this is legal. Now watch this. N over n is 1, and then I've got a 1 over n there. And then I've got 2n over n is 2 plus 1 over n. Let's see what we get as n goes to infinity. This goes to 0, this goes to 0, this goes to 0. So what we get is 48 minus 4 minus 4 thirds times 1 times 2. So you have 44 minus 8 over 3. So I get 124 over 3, or if you prefer 41.3 repeating. What's that? Those are square units. That's the area here. That's the area under this curve. So what you do if you're trying to find the area under the curve using the limit definition is you sketch the region, and then you start computing a finite sum, any finite sum. You can do upper sums, lower sums, left endpoint, right endpoint. I tend to use the right endpoint because it's a simpler formula. Then I find the area using that right endpoint. That's f evaluated at the right endpoint times delta x. you should see i's and n's everywhere. Distribute, simplify, and then the total area is the sum of all of those little area pieces. This is just one of n rectangles. You want to add those together, so that's this. And then you simplify this using your summation formulas and the properties of summation. So I've got a difference here. I've got this minus this minus this. Well, I can just add these, and I can subtract the sum of these and subtract the sum of these. And I've got a formula for a constant here. If I add a constant to itself n times, I just get that constant times n. I bring this constant down. The sum as I goes from 1 to n of the i's is given by this. Thank you, Gauss. And then I bring that constant down. The sum as I goes from 1 to n of the I squareds turns out to be this. So we have this formula, this area, in terms of n only right down here. So if I had a million rectangles, I could plug in a million and I'd have the area. If I had 10 rectangles, I could plug in 10 and I have the area. This is great. It tells me the area for however many rectangles I have. Then I say, I'm going to take the limit as the number of rectangles goes to infinity. That's going to give me the exact area under this curve. So we take the limit of this result and we get this. Now, if you're not really sure about this idea, let's look at it. Let's think about it. Let's say I've got the interval from a to b of some function. If I just split that into two subintervals, and I find an area there and an area there, that's actually pretty good as far as an estimate of area under the curve. If I want a better estimate, I'll just take more rectangles. Let's do that instead. If I want an even better estimate, I take more rectangles. There are actually some really beautiful little apps online. I think if you search for desmos.com, you can see what happens as the number of rectangles goes to infinity. Just search for Riemann sums or area with finite sums. But you can see that area, that error shrinking. I'm not doing it justice with my little picture here. But as n goes to infinity, the error gets smaller and smaller. In the limit, it turns out you get the exact area, which I think is pretty cool. Now there's actually a shortcut for this called the fundamental theorem of calculus. We don't generally have to do limits every time. And I will show you that in the next video.